have you ever stopped to think about what's really going on when you flip a switch? I mean, behind every screen, every motor, every single light, there's a hidden set of rules, a language, really. And today, we're going to crack open the code using a few classic engineering problems to light the way.
I mean, really think about it. We use this stuff every single day without a second thought. But how does a hunk of metal start spinning with incredible force? How does electricity turn into pure, blistering heat? Well, the answers aren't magic, it's physics. And honestly, it's pretty beautiful.
So, we're going to look at what might seem like a bunch of boring old exam questions, but I want you to see them as puzzles, because each one we solve unlocks another secret, another piece of the story of how our entire modern world gets its power. Okay, let's dive in.
First things first. Before we can even talk about circuits, we have to understand the invisible stage where it all happens. We're talking about electric and magnetic fields. These are the unseen forces that are literally all around us, filling the space in every wire and every single component.
So, to picture these electric fields, we use something called field lines. And they follow some really simple, and I mean unbreakable, rules. They always flow out from a positive charge and into a negative one. Where they're bunched up, the field is strong. Where they're spread out, it's weak. And here's the absolute kicker. They can never, ever cross. That one simple fact is why everything from a tiny chip to a massive power grid actually works.
Okay, so what happens when you take one of those fields, a magnetic one, and run an electric current through it? Well, you get force. You get actual physical motion. This simple-looking formula, which comes from Fleming's left-hand rule, is the basic recipe for turning electricity into movement. This right here, this is why a motor spins.
And boom, here's the proof. When we actually solve one of our puzzles, plugging in the numbers for a wire with some current in a magnetic field, we get a real answer, a tangible, physical push of 1.2 newtons. That force, born from an invisible field, is how we start to harness electricity to do real work in the world.
Now, I know what you're thinking. That number looks tiny, right? It's a fraction of a newton. But here's the secret sauce in things like electromagnets and motors. They don't just use one wire. They use thousands of coils of wire, all wound together. And all those tiny individual pushes add up into one seriously powerful force.
You know, to make sense of all this, engineers came up with a great analogy. They talk about magnetic circuits. Think of it this way. Just like an electrical circuit has a flow of current, a magnetic circuit has a flow of something called magnetic flux. It's really just a way of counting up the total amount of magnetic field you've got passing through an area to do a job.
And when you create that magnetic flux by running current through a coil of wire, what we call an inductor, you're actually storing energy. In this case, it's 2 joules. You can literally think of an inductor like a compressed spring. The energy is just sitting there, stored in the magnetic field, waiting to be released. This is an absolutely crucial idea for how things like power supplies and transformers work.
All right, we've got the invisible forces down. Now let's see how those electrons actually behave once they're inside the wires. You can think of a circuit like a highway system for electrons. And just like any highway, there are some very strict traffic rules you have to follow. And the biggest, most important rule on the road is Kirchhoff's second law. It sounds complicated, but it's really just the law of conservation of energy in disguise. All it says is that for any complete trip around the circuit, all the energy the battery puts in has to get used up by the stuff in the circuit. Energy in has to equal energy out. Nothing just vanishes.
Now here's the formal textbook way of saying it. Electromotive forces. That's just a fancy term for the energy the battery supplies. And voltage drops. That's the energy the components like resistors or light bulbs use up. So yeah, the words are a bit intimidating, but the idea is still that same simple concept. What you put in, you must get out.
And the beauty of these laws is that they let us predict exactly what's going to happen. Let's take this puzzle. 10 little batteries hooked up to a resistor. How much current is flowing? Well, we just follow the steps. First, add up all the voltage from the batteries. Easy enough. Then, add up all the resistance. And don't forget the tiny resistance inside the batteries themselves. Finally, use the famous Ohm's law, and there's our answer. 2.5 amps. See? No magic, just logic. So where does all that energy go? Remember our question from the very beginning about how a heater works? Well, Joule's law is the answer. It's the rule that connects electrical power directly to the heat it creates.
When electrons struggle to get through a resistor, that energy doesn't just disappear. It gets converted straight into heat.
And we can figure out exactly how much heat. For our puzzle, with a big 3-kilowatt heater running for just 20 minutes, it pumps out a whopping 864 kilocalories. To put that into perspective, that's roughly the energy in 2 big cheeseburgers. All of it converted from electricity into raw heat just to make your room cozy.
Okay, we've wrestled with the invisible fields, and we've learned the laws of the road. Now let's look at the actual players in this game, the physical parts and the unique pulse of the alternating current, or AC, that powers pretty much everything in our home.
Capacitors are a huge deal. They act like tiny little batteries that can charge and discharge incredibly fast, but they're not all the same. As you can see here, you've got different types for different jobs. But a ceramic capacitor, that's like the Swiss Army knife of capacitors. It's a great all-arounder, and it's not polarized, which means you can't hook it up backwards. That makes it super versatile.
Let's talk about the AC power from your wall. You know, it's not that perfectly clean, smooth sine wave you see in textbooks. A real-world electrical signal is actually, well, it's messy. It's a mix of things. You've got your main wave, the fundamental one, but on top of that, you've got all these little echoes, these harmonics, and sometimes even a little bit of steady DC current mixed in for good measure.
And that messiness leads to a really common point of confusion. We all talk about our power being, say, 220 volts or 120 volts. But that number you hear all the time, that's really just a kind of average. It isn't the whole story.
Get this. The true effective power, what engineers call the RMS value, is actually higher. In this case, it's around 245 volts. And the RMS value is what really counts. That's the number that tells you how much work the electricity can actually do. It's the real muscle behind the current.
And finally, we get to the boss battle, the RLC circuit. This is where it all comes together. A resistor, an inductor, and a capacitor, all in one circuit, all doing their thing at once. It looks super complicated, but the idea is actually a tug of war. The inductor and capacitor pull in opposite directions. So first you figure out who's winning that tug of war. Then you combine that with the resistor's drag to get the total opposition of the circuit. We call that impedance. And once you have that, finding the current is easy. This is it. This is peak circuit analysis, predicting exactly how all the pieces will work together.
So let's just pull back for a second. By working through these puzzles, we've basically unlocked the 4 fundamental building blocks of circuit theory. We've got the invisible fields and forces that create motion. We've got the simple laws that act like traffic cops for electricity. We've got the physical parts that store and manage that energy. And we've got the messy, dynamic, powerful waveforms of AC power. These aren't just abstract ideas or lines in a textbook. These are the literal tools that engineers use to design every single piece of technology that surrounds you right now. They're the language of innovation. So the only question left is, now that you understand the rules, what are you going to build with them?